Hi guys, this is Srinivasa once again for you. Today I am going to teach you the integer programming. It's a bit difficult task for you, but we are going to solve this. We have the LP in the form of maximum z equal to x1 plus x2 subject to constraints 3x1 plus 2x2 less than or equal to 5, x2 less than or equal to 2 with the non-negative restrictions x1 comma x2 greater than or equal to 0. Here we have to observe x1 x2 both are integers. So for this integer programming, we have to follow three major methods. So the first method is simplex method. First we have to apply the simplex method. After that, we have to check whether the x1 x2 are integers or not. If x1 x2 are integers, then the solution is optimum. Otherwise, we have to introduce a GOMORIAN method. If the GOMORIAN method is, after applying the GOMORIAN method, we get some sort of a negatives, again we have to apply, that is dual simplex method. After this, again we have to apply the simplex method, the tempo will continues. So the first, I am going to apply the simplex method for the given LPP, that is this one. So in the previous classes, I discussed about the simplex method. Again, I am going to teach you the simplex method once again for you. So the first step for this constraints is change the inequalities into equalities by introducing slack variables. So that is, the solution for this is as follows. Change the inequalities into equalities by introducing slack variables, that is 3x1 plus 2x2 plus s1 is equal to 5, x2 plus s2 is equal to 2. So straight away I will move on to the first iteration table. That is, we have the cost of the basic variable cb, yb, xb. We have the variables x1, x2, we have s1 and s2. And we have the auxiliary function cj, that is the cost of the variables, that is for x1 we have 1, for x2 also 1, that is 0, 0. In the first equation, we introduce the slack variable s1, the introduced variable cost will be 0, and for the second one we introduce s2, the cost will be 0. Now that is x equal to b, that is the b is 5 and 2. Now I am going to represent the total matrix here. That is, for the coefficient of x1 we have 3, for x2 that is 2, s1 we have 1 and we don't have s2. In the second one we have x2, so that we don't have x1, that is 0, x2 is 1, s1 we don't have 0 and s2 that is 1. After this we have a massive 3 steps for this. That is, we have the first function, that is maximum z equal to summation cb into xb, that equal to 0 into 5 plus 0 into 2, that is the value is 0. And we have a condition for zj, that equal to summation cb into xc. 0 into 3, 0, again 0, the value should be, and when we are going to multiply with 0, the value should be 0s. After this we have our net evaluation condition, that is, the net evaluation condition is all of you zj minus cj greater than or equal to 0. That is 0 minus 1, that is minus 1, 0 minus 1 again minus 1, and 0 minus 0 again 0, and 0 minus 0 again 0. But all of you, in this case, the net evaluation conditions are not satisfied, that is minus 1 and minus 1. So we have the step, that is minus of maximum here. But there is a tie for this, that is minus 1 or minus 1. If you observe this, we are going to get the key element from 3 and 0. If you observe this, we have to get the key element as 2 and 1. So after the next step, make the key element into unity by dividing itself. So I am considering this. Why? Because we have a 1 here. So without loss of generality, I am taking this minus of maximum. Okay, so after this we have a minimum ratio rule. That is, the minimum ratio rule is xb by xj. What is xj? This arrow will indicate x2. So this is all about xb by x2, that is 5 by 2, that is 2.5, 2 by 1, that is 2. So in this case minus of maximum, in this plus of minimum. So what is the plus of minimum from 2.5 and 2? Obviously 2. If you are going to combine these two, the key element is 1 obviously. Because of this key element only, we are not going to satisfy this net evaluation condition. In simplest method, after finding this, we have the second iteration table. Make the key element into unity by dividing itself. x2 is incoming vector, s2 is outgoing vector, the cost of x2 is 1, and make all the elements in the key column has to be 0. Now, the second iteration table is as follows. That is, the second iteration table. As usual, we have CB, YB, XB, X1, X2, S1, S2. That is, there is no changes for S1, the cost will be 0. Here, X2 is the incoming vector, S2 is the outgoing vector. Then X2 will be here. The cost of X2 is 1. And that is Cj, we have 1, 1, 0 and again 0. Make the key element into unity by dividing itself. So obviously the key element is 1, no changes whatsoever. Simply we have to copy this. So that is 2, 0, 1, 0, 1. Now we have to make all the elements in the key column has to be 0. So that is we have to make this 2 as 0. So we have to go for some sort of a rough work. That is, first we have to write that row 5, 3, 2, 1, 0. With the help of the key row, we are going to make this values as 0. That is 2, 0, 1, 0, 1. We have to get 0 here. So we have 2. So if we have 2 here, then obviously we are going to subtract. So without loss of generality, I am going to multiply with 2. For example, if you have a 4, multiply with 4 obviously. So that is 2 2s are 4, 0, 2, 0 and 2. I am going to subtract these 2. 5 minus 4, that is 1. 3 minus 0, that is 3. 2 minus 2, that is 0. 1 minus 0, again 1. 0 minus 2, that is minus 2. I am going to represent this entire row in the first row. That is 1, 3, 0, 1, minus 2. And again we are going to apply the same formulas. That is the maximum Z. The maximum Z formula is summation CB into XB. 0 into 1, 0 plus 1 2 Z2. And we have a ZJ notation, summation CB into XJ, CB into XJ. 0 into 3, 0, 1 into 0, that is again 0. 0, 1, that is again 0. 0 into minus 2, 0, 1 into 1, again 1. We have a net evaluation condition, Zj minus Cj greater than equal to 0. So that is, Zj means this one and Cj. 0 minus 1, that is minus 1. 1 minus 0, that is, 1 minus 1, that is 0. 0 minus 0, 0 and 1 minus 0 again 1. In this case also, the net evaluation condition is not satisfied, that is minus 1. The same thing all of you, that is minus of maximum. We have to consider minus of maximum here. What we did in the first table. So that is minus of maximum. Again, we have a minimum ratio rule, that is xb by xj. That is xb by xj. xj means x1. That is 1 by 3, 2 by 0. 1 by 0 is undefined. Okay, so obviously we have to consider plus of minimum. So obviously we have plus of minimum is 1 by 3. So the key element is 3 here. These are the key elements. So in the previous problem we got 1 as the key element. In the second table we got 3 as the key element. In the same way, we have to make this key element into unity by dividing itself. That is, I am going to divide this entire row by 3. And x1 is the incoming vector, s1 is the outgoing vector. The cost of x1 is 1. And make all the elements in the key column has to be 0 in the third iteration table. That is, the third iteration table is as follows. CB, YB, XB, X1, X2, S1, S2. So that is, so there is no changes for x2, the cost will be 1. For this also, x1 is the incoming vector, that is x1 is the incoming vector, s1 is the outgoing vector. So x1 will be here, the cost of x1 is 1. Now we have to make this key element as unity by dividing itself. So the key element is 3. I am going to divide this entire row by 3. That is 1 by 3. 3 by 3, that is 1. 0 by anything again 0. 1 by 3 and again minus 2 by 3. And make all the elements in the key column has to be 0, all of you. So obviously here the key element is 1 and all the elements in the key column has to be 0, that is 0 here. Obviously the value is 0. So it's not necessary to make the value 0. So simply I am going to write the values there. So that is 2, 0, 1, 0 and 1. That is again we have a Cj 1, 1, 0 and again 0. Here we go, the same tempo. The maximum of z 1 by 3 plus 2. That is 1 by 3 plus 2 is obviously 3 2 just 6 plus 1, that is 7 by 3. Zz summation Cp into xj 1 plus 0, that is 1, 0, 1 1 is 1. 1 by 3 plus 0 again 1 by 3. Minus 2 by 3 plus 1. Minus 2 by 3 plus 1, that is 3 minus 2, that is 1 by 3. And we have a Zj minus Cj condition. That is the net action condition Zj minus Cj greater than equal to 0. 1 minus 1, that is 0. 1 minus 1, that is 0. 1 by 3 minus 0, that is 1 by 3. And 1 by 3 minus 0 also 1 by 3. All of you, here the net action conditions are satisfied. But if you observe the question, x1, x2 are positive integers. So this problem, we have to prove that the x1, x2 values are the positive integers. So the value of x1 is 1 by 3. Is not a positive integer. So for that reason, we are going to apply a GOMORIAN method. Why we have to use a GOMORIAN means x1 is 1 by 3 is not a positive integer. So for that reason, we are going to apply a GOMORIAN method here. That is GOMORIAN method. So for this method, we have to consider the maximum of xb's. That is the maximum of xb's. Luckily we have the fraction values only. That is 1 by 3 comma 2. That is 1 by 3. That is the fractions we have to consider. Okay. So that is a 1 by 3 means all of you. So we are going to write this entire data in terms of a GOMORIAN method. Okay, that is the GOMORIAN condition is the GOMORIAN condition z1 equal to minus fk naught plus fk1 x1 plus fk2 x2 plus so on. Let us assume that the value that is fk naught equal to 1 by 3. So here we are going to consider the fraction values only. Okay, so that is fk naught equal to 1 by 3. So I am going to represent this entire row in terms of fraction values. So that is, I am going to substitute here z1 equal to minus as usual there fk naught is we consider 1 by 3 plus fk1 x1. So if you observe this is all about the 1 by 3 row. In this we have to consider only the fraction values. So 1 is not a fractional, so we have to consider 0. That is 0 into x1 plus, for x2 also we don't have a fraction, that is 0 into x2 plus 1 by 3 is a fraction, so 1 by 3 into x3 plus, so all of you, this minus 2 by 3 can be written as minus 2 times of 1 by 3. So only the positive fractions only we are going to take, that is plus 1 by 3 into x4. This equation can be written as minus 1 by 3 is equal to minus 0 into x1 minus 0 into x2 minus 1 by 3 into x3 minus 1 by 3 into x4 plus z1. So I am going to take this entire data to the left hand side. So now we can treat it as the equation 1. Now I am going to replace this equation 1 in the above iteration table. So we have the iteration table. Now I am going to introduce this equation 1 in this iteration table. So just listen here. That is, I am going to replace the total equation here. is, we have a G1 here. The introduced GOMORIAN cost should be 0. Now I am going to represent this. So that is minus 1 by 3 here. That is minus 1 by 3. The cost will be 0, whether it is a positive 0 or a negative 0, no problem whatsoever. 0, 0, minus 1 by 3, and again minus 1 by 3. All of you, we have a G1 here, so we have to represent the GOMORIAN G1. The introduced GOMORIAN cost should be 0, the value should be 0. In the first equation, we don't have the GOMORIAN, so obviously 0. In the second one also, we don't have the GOMORIAN 0. In the third equation, we have a G1. The cost of G1 is, the coefficient is 1. Now we are going to apply the formula. So that is maximum of Z equal to summation CB into XB 1 by 3 plus 2. That is 1 by 3 plus 2, that is 7 by 3. ZJ, that is summation CB into XJ 1, 0, 0, that is 1. 0, again 1. 1 by 3 into 1, that is again 1 by 3 plus 0, that is 1 by 3. That is minus 2 by 3 plus 1. Minus 2 by 3 plus 1, that is 3 minus 2 by 3. That is again 1 by 3. That is again 0 and again 0. We have an activation condition. The formula for the activation condition is Zj minus Cj greater than or equal to 1 minus 1, 0. Again 1 minus 1, that is 0. 1 by 3 minus 0, that is again 1 by 3. Again 1 by 3 and again 0 minus 0, 0. Here the activation conditions are satisfied. X2 we got as an integer finally, but X1 is not an integer. For that reason, again we will move on to the next step. So make it a point, all of you, when we are going to apply our GOMORIAN method, obviously you have to apply dual simplex method here. For dual simplex method, all XB's should be positive. So in the question, X1, X2 both are integers given. So X2 is an integer we got finally, but X1 is not an integer, and also XB's are negative. For that reason, now we are going to apply dual simplex method. That is, the dual simplex method conditions are we have. That is minimum of XB's, where XB's are less than 0. So obviously we have a minimum value is obviously minus 1 by 3. That is, the XB's are 1 by 3 to minus 1 by 3. Obviously minus 1 by 3. So these are the first condition for dual simplex method. That is, and the next one, that is maximum of Zj minus Cj by minus 1 by 3 rho. The next step. In this dual simplex method, we don't have minimum ratio rule. So these are about minus 1 by 3. This minus 1 by 3 rho, we have to divide with this. So that is minus 1 by 3 means this one. So we are going to find the key element in this row. So the next step is maximum of Zj minus Cj by minus 1 by 3 rho. That is maximum of Zj minus Cj is 0. 0 by 0 undefined. Again 0 by 0 undefined. 1 by 3 by 1 by 3. That is again minus 1. Again 1 by 3 by minus 1 by 3. Again minus 1. And 0 by 1, that is undefined. In this, the maximum is obviously we have minus 1. Okay, so this minus 1 means this one only, these two only. So for example, if you consider this, we have to get the key element as minus 1 by 3. If you consider this also, we can get the value as minus 1 by 3. After this step, we have to make the key element to unity by dividing itself and make all the elements in the key column has to be 0. So obviously we got 0 here, but in this case we don't have. So without loss of generality, I am taking the value as this. That is minus of maximum like this. In this method, make it a point, in dual simplex method, we don't have a minimum ratio rule. If you combine these two, minus 1 by 3 is the key element. So as usual, S1 is the incoming vector, G1 is the outgoing vector, the cost of S1 is 0, and make all the elements in the key column has to be 0, and make the key element to unity by dividing itself. So in order to divide this value with minus 1 by 3, it's better to multiply with minus 3. Then the next iteration table is as follows. That is, we have the iteration table CB, YB, We have variables x1, x2, s1, s2 and the GOMORIAN G1. By a Cj values are we have 1, 1, 0, 0 and again 0. There is no changes for x1, x2. Copy this. The cost will be 1 and again 1. And for this, in this case, s1 is incoming vector and the cost should be 0. Now we have to make the element to unity by dividing itself. So obviously, in order to divide with 1 by 3 minus 1 by 3, it's better to multiply with minus 3. Minus 3 into minus 1 by 3 minus into minus plus 3 gets cancelled. The value should be 1. 0 and anything again 0. 0. Obviously 1. This is all about 1 and minus 3 into 1 again minus 3. We have to make all the elements in the key column has to be 0. Obviously, we got the value is 0 here. Without loss of generality, I am going to write all the values here. That is again, take a part and that is 2, 0, 1, 0, 1, 0. Now we have to make this value as 0. So we have to take some sort of rough here. So first we have to represent the entire. That is again 1 by 3 we have 1, 0, 1 by 3, minus 2 by 3, 0. With the help of the key row, that is the key row is this one. There is again right now that is 1, 0, 0, 1, 1, minus 3. We got 1 by 3 here. To make this value as 0 without loss of general, I am going to multiply with 1 by 3. 1 by 3 into 1 that is 1 by 3. I am going to subtract 1 by 3 minus 1 by 3 that is 0. 1 minus 0 obviously 1. 0 minus 0 again 0 that is 1 by 3 minus 1 by 3 that is 0. Minus 2 by 3 minus 1 by 3 that is minus 1. And finally 0 minus into minus plus 3 into 1 by 3 3 gets cancelled. The value is 1. Now I am going to represent this entire row in the first row that is again 0. 1, 0, 0, minus 1 and again plus 1. So the next table, that is, we have all the formulas here, that is maximum of z. Max z equal to summation Cp into Xb 0, 1 to z2, zz that is 1, 0, 0 that is 1, again 1, 0, minus 1 plus 1, 0, 1 plus 0 again 1. And we have an intervention condition Zj minus Cj greater than or equal to 0. 1 minus 1 that is 0, 1 minus 1 that is 0, 0, 0, 1. All of you, the net intervention conditions are satisfied. All xb's are positive. Make it a point. x2 is 2 is a positive integer. x1 is 0 is a positive integer. Hence, the solution is optimum. For example, if the values are not at all in terms of integers, again we have to go for the GOMORIAN. Luckily, we got the values x1 and x2 are integers. So, and hence we are going to write the conclusion for this. The conclusion is all of you. X1 we got x1 as 0 and x2 is 2 and maximum z is 2. These two are positive integers. This is all about the integer program. If you want to check, you can check. The given objective function is all of you. We have an objective function max z equal to x1 plus x2. If you put x1 equal to 0 and x2 equal to 2, that is 2. So the max z equal to 2, we got the max z equal to 2. Here we go, we have a max z equal to 2. Hence, the solution is optimum. Thanks a lot for watching this video. Thank you.